Okay. So hi everyone, thanks for joining today. My name is Andres Ferraro. I'm a postdoc researcher in Mila and McGill University, Montreal. So welcome everybody to the second edition of Latin America BISH Bash meeting. For those that are joining for the first time, the goal of these meetings is to connect different communities of researchers, students, and engineers from Latin America related with sound and audio signal processing, and also to reduce the distance between the communities with the rest of the world. So in this edition, it's hosted by the group of audio processing from Universidad de la República from Uruguay. Today we are going to have 4 presentations from current and former members of the group. Each presentation will be around 15 to 20 minutes, including some time for Q&A, and if we have time, we will also have some Q&A at the end. So then in the end, we are going to have a networking session so you can interact, and and three of the talks are going to be in English and one is going to be in Spanish. If at any point there is something that's not clear regarding the language, you can always ask in the chat and we will try to reply. So now without further delay, I'm going to leave the floor to Martín Rocamora, that is going to give the first presentation. So Martín, it's all yours.
I'd like to see. I'm sorry, I will share the audio too. All right, that's okay. And this is fine too. Okay, and I'd like to see your faces. I don't know how to do that. All right, there, fine. That's okay. So I'm very happy to be here with all of you. It's a really nice idea, and I miss you all, guys. I hope we were all together, not virtually. We had the Brazilian Symposium on Computer Music last week, and it was nice to meet some of you, some of our colleges in Brazil. I'm gonna start this meeting by talking about some particular research we've been doing in Facultad de Ingeniería, Universidad de la República, in our group during the last few years. And well, first of all, I'd like to show you our alma mater. We all of the presenters here have been studied and also have been teaching in this place. So some of us are still there teaching and doing research. So I'm gonna first start by talking. Well, by the way, if some of you find the things we are going to talk today interesting and wanna stay some time here with us, you're more than welcome. In the past, we had some students from Brazil, and it was very nice experience, at least for us. Some of them are here, so they can tell. And okay, so talking about the research we do, I'm gonna talk about MIR, music information retrieval. This is one of the main research fields we addressed in our group. I guess most of you are aware of what's MIR, but anyway, for those who don't, it's the development of computational tools for processing, searching, organizing, and accessing music-related data. Be it lyrics, editorial data, the playlist, audio, whatever you want. But at least in the past, most of the systems that were developed rely on audio. And sorry, I have some notifications here. And all right, that's fine. I was saying that most of the system developed rely on audio, at least in the past, and that's why most of the work with it was based on audio, right? So the idea is to you start from a low-level representation of the audio signal, either waveform, the spectrum, or you name it, or some low-level descriptors, and then you try to go up to higher-level concepts, musical concepts, and this is done essentially by using signal processing and machine learning, right? And a lot of machine learning in the recent years. Okay, so in this context, we were from the beginning. I didn't say that we've been working in this field for, let's say, more than about 15 years, and it seems to be a lot. And from the very beginning, we were interested in expressive music performances, right? As I guess you know, an accomplished musician can always shape various parameters when playing a musical piece, like tempo, timing, dynamics, intonation, articulation, whatever. And so this is something that's quite interesting to look at. And we start in our early works, we devote a lot of efforts into studying pitch, in particular trying to represent and to track precisely the pitch variations. And so we developed some tools in order to do that. This is an example of one of the, let's say, the maps we built of pitch contours. I mean, I say precise because we try to represent those pitch variations precisely and be able to track them with some kind of detail, right? And so this is an example of what's represented here. I'm going to play an audio example of this. Let me know if it's okay. So it's a kind of weird kind of music. It's three singers singing together. And you see there are actually two melodic lines, and they vary a lot in pitch. I'm not going to talk about this today because the music dimension we address in our more recent work, it's rhythm. We try to discover patterns and structure from doing audio analysis, focusing on the rhythmic properties of the audio. In particular, we deal quite a lot with micro timing, which means the small scale temporal deviations of the events in the musical surface with regards to an underlying metrical grid, right? Imagine you tap your feet to the music. So there you have the reference. And so the onsets or the notes could be either before or after, not necessarily at the beats. And also, it's also quite interesting to look at the differences between musicians playing together at a certain temporal position, right? So we're going to talk a little bit about this. Okay, and this kind of research that focus on particular dimensions of music, and in some cases, subtle differences between performances or subtle differences between recordings is not possible if you are not if you don't have a strong relationship with either musicians or people that comes from the musicological field. And here we are quite lucky that to have a long-standing and strong relationship with people from the School of Music. And so our approach is to work together in order to bring as much as musical knowledge as possible to the methods. In a kind of, I always show this diagram because I like it. It's the way I think we work actually. And try to seek and try to formulate musically relevant analysis problems, talking to them or talking even to the practitioners, to the musicians that practice this particular kind of music we are dealing with, and then try to convert those problems into engineering formulations, right? And so our motivation in the last few days, in the last few years, was the analysis of a particular kind of music we have here in Uruguay. If you happen to come to Montevideo, you'll probably see people playing drums in the streets. That's I guess it happens in Brazil and other parts of Latin America. And so I'm gonna play a video about this to give you some sort of a sense of how it goes. The video is not very good. The audio is not very good, but it's natural, right? It's how it happens. Fine, so I kind of see you again. Yes, there. Oh, sorry. So this is part of long-standing tradition of people of African descent, and it's still a kind of symbol, identity symbol for them, playing drums in the streets, right? And so, well, you have let's have a glance of how the rhythm is. You have a Chico drum that plays an invariable pattern at a high rate. It's like the timekeeper. You also have the clave pattern, right? The one when you play with a stick into the drum, in the shield of the drum. And this pattern you may probably know from this and other kinds of music, like ka 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 ka, right? And then you also have two other drums, the repique, which is essentially improvised but has a characteristic primary pattern, like cow 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 cow. Okay, and also you have the piano, which is the lowest sounding one, and its pattern it's also very complex, has many variations, but it's the skeleton of its pattern is aligned with the clap and sounds like tu tum tu tumba. Okay, have some examples here, but we don't have time to listen to them. Okay, so what we did at the very beginning was to do some recordings. We also released data in order to do research, the data we were using for research, multi-track and audiovisual data sets, also with labels that are essential for doing some kind of evaluation. And we address several kind of problems, right? First of all, some of them were focused on the analysis and the discovery of the rhythmic patterns that are present in that kind of music. Okay, so we first did our automatic beat and downbeat tracking. This was quite interesting because the syncopation and the particular features of the rhythm make it quite challenging for some of the traditional approaches for doing beat and downbeat tracking. And after that, we did the analysis, as I said, the analysis and discovery of rhythmic patterns. For instance, if you have this audio signal and then you have the beats and the downbeats, then you compute some kind of accentuation feature, and you may build this kind of map in which you have, this is the beat in the horizontal axis. Sorry, this is the rhythmic cycle or the bar in the horizontal axis, and in the vertical axis you have how the rhythmic pattern that it's played in this time slot. Okay, and so we can group these rhythmic patterns by their similarity. So this is a kind of map of a whole performance in which you can see that there are different kind of patterns some that are bass rhythmic patterns, some others that are used for conveying some kind of information to the other members of the group. And by using these rhythmic patterns, we can also identify, or if you group them in some kind of representation like this one, you can identify different styles, for instance, different performers or different performance styles, schools, let's say, that you have in this rhythm. Okay. And we also, well, this is another example of this kind of discovery of rhythmic patterns. These are the clave pattern that I mentioned before. It's actually not played in this way. What we actually do is we play many variations of this clave pattern, and these are some of those variations that are discovered or I mean, we come up with them from the analysis of the data. And then talking about the micro timing analysis, remember it was those small scale temporal deviations with respect to the metrical grid. We consider some ostinato patterns that are always the same, in particular the Chico and Repique one. And we did some analysis in order to see where the onsets were actually located. And you see that they are, for the Chico drum, for instance, if the grid would be isochronous, you'd have the onsets mostly aligned here in 75% and here 50%. But you can see that the location of the onsets is somehow compressed in time, right? And something similar happens with the other rhythmic pattern, okay? And this is not particular of this recording, or it's somehow it's a feature of the rhythm, okay? It's let's say it's somehow always present. So it's nice to see that it's actually a fundamental part of playing the rhythm. And finally, we put this and other kinds of information together, like the asynchronous between musicians playing together, or dynamics. We compute dynamics from the audio and also from the video. I don't know if you're looking at the video now. Yeah, okay. I always get confused with the Zoom. Okay, so we put all this information together and try to address higher level musical questions, like how musicians negotiate tempo and dynamics. And well, this was quite an interesting challenge. And we also, as I say, we measure these temporal deviations. Okay, so we did some work in the context of a broader initiative that also involved jazz and djembe music from Mali, and we tried to study the musicians' preferences for those deviations, right? And this was quite interesting too, because the question arises if those deviations that you measure are actually heard or are actually important in this musical form, right? And well, we also tried to extend and to improve the kind of tools we were developing by addressing Afro-Brazilian samba in collaboration with our partners and beloved friends in Brazil. And Magda also took part. Well, Magda actually was present at the very beginning in one of the pictures I showed when I talk about the recordings, right? And so, well, some other data sets of samba music were gathered and annotated. This one here is really great, and it's available for doing research. And we address other kinds of problems, like jointly tracking beats and micro timing, doing all these things together. And finally, I wanted to mention that we are doing a collaboration with some Argentinian researchers from the la Universidad de La Plata. And we try to extend this kind of things for the analysis of Argentinian tango from historical tango recordings. We also focus on expressive timing, and we did correlation of tempo curves at different tempo scales. And we address in this paper here the analysis of the style of Aníbal Troilo and compare his style with other tango orchestras, and this is actually an ongoing research. Okay, and finally, just want to say that gradually all these things are being integrated into a toolbox that we are working now. We have a research project now going on to improve these tools and also to increase the number of recordings. We have a set of 75 minutes of new recordings that are quite nice, and we are annotating that. And I invite you to look at these tools, and I think that's it.
Great.
How was the time? Not so
Perfect.
far.
We have a couple of minutes for questions. If yeah, someone can write in the chat, or yeah, just.
And I always finish with this picture that says that that Candombes is still active here, is still in development, and we have a lot of things to do here with this kind of music, and I guess with the other music kind of music I mentioned. Sorry, Andres, you were.
I can ask you. I'm interested in this tango work.
Well, that's what I mentioned, that I want to talk to you about that.
Okay.
Yeah. So yeah, that's it.
Okay. So let's move then to the next presentation. So the next one is going to be by Ignacio Irigaray. So Ignacio, all yours.
Okay, first I will speak in Spanish, but the slides are in English, and you can ask me questions in English, Portuguese, or Spanish. Y bueno, nada, voy a compartir.
Or in French too.
No. Ok. Ahí. Bien. ¿Ahí se ve la presentación?
Yep.
Sí, perfecto. Bien. Bueno, yo también soy de la Universidad de la República, de la Facultad de Ingeniería. Y bueno, venía a presentar algunas cosas que estoy haciendo en el doctorado. Soy estudiante de doctorado. Estoy trabajando en colaboración con el Centro de Documentación Musical Laura Gestarán, y mi tutor es Luis Wagner, que anda por ahí. Y el trabajo de la tesis es sobre la restauración de grabaciones de audio, y más precisamente la restauración de grabaciones musicológicas o de archivos musicales. Entonces, si les parece bien, arranco contándoles un poco el contexto de este trabajo, de qué se trata el CDM, el trabajo de Laura Gestarán, y cuál es el acervo que tiene. ¿Sí? Entonces, Laura Gestarán fue un destacadísimo musicólogo, fue pionero en lo que es la musicología en el Uruguay, nació en 1913 y murió en el 66, murió realmente muy joven. Lo que más destaca de sus trabajos es la impresionante colección de grabaciones de músicas tradicionales que realizó entre 1943 y 1966. Recorrió todos los ámbitos culturales del país y generó un acervo de más de 3.000 registros, que es fundamental para entender quiénes somos en materia musical acá en Uruguay. ¿Sí? Todo ese material quedó en custodia de la familia desde el 66 hasta el año 2002, que que el Ministerio de Educación y Cultura adquiere esos materiales y con esos materiales funda en el 2009 el Centro Nacional de Documentación Musical Laura Gestarán, ¿sí? Y el objetivo del Centro de Documentación Musical es más amplio que solo la custodia de las grabaciones de Gestarán, sino que se ocupa de recoger toda la memoria de la música uruguaya, ¿sí? Pero la piedra fundamental es el material de Laura Gestarán. Entonces, ahí en el CDM se conservan los registros sonoros en su soporte original, de cinta magnética, ahí a la derecha, y después hay algunas grabaciones, las primeras que hizo estarán en discos de acetato, en discos instantáneos, como el que se muestra a la izquierda. Por otro lado, también se dispone de una digitalización completa de todas las grabaciones, que es tiene una historia ahí un poco enredada, de un respaldo que tenía Gestarán se hizo una copia en cassette C90, eso se pasó a DAT y finalmente se entregaron unos CDs, y todo eso por iniciativa del Museo de Estocolmo, o sea que la calidad de las grabaciones, de las digitalizaciones que se disponen no es la mejor, y bueno, es un objetivo del CDM y en colaboración con la facultad, es lograr volver a digitalizar las cintas originales y mejorar un poco la calidad de esos archivos. ¿Sí? Bien, entonces un poco hablemos de las grabaciones analógicas. ¿Sí? La podemos pensar como una transformación de las ondas sonoras que se propagan en el aire en unas ondas que se almacenan en un medio físico que está en movimiento. ¿Sí? Un disco, una cinta. Entonces, ahora les propongo escuchar una grabación de Amalia de la Vega, del año 49. En el año 49 Amalia de la Vega era casi desconocida, después ella tuvo toda una carrera de música popular profesional. Esa grabación fue hecha originalmente en un disco instantáneo. Ahí vamos a escuchar ruidos de superficie de la púa cuando se mueve, vamos a escuchar clics y pops, vamos a escuchar una resonancia, sobre todo en la voz de Amalia cuando canta más fuerte, va a haber problemas de saturación, y van a haber problemas en la base temporal, en la base de tiempo, y en esos problemas va a ser en los que nos vamos a concentrar en la charla y en los que yo más estoy trabajando ahora en el doctorado. Entonces, escuchamos, me avisan ahí si se escucha bien.
Deje la vela enramada, cuando la criolla turbada al suave calor de un beso sonríe con embeleso el galán de fa.
Bien. Nada, vieron que tiene un montón de defectos, ahí sobre el final hay un defecto ahí en la base temporal que hace que suba como un semitono y después baje, que eso nunca lo haría mal, ¿sí? Y bueno, antes de meternos en las técnicas para resolver esos problemas, hablar un poco de la grabación, ¿sí? En la imagen de la izquierda tenemos ahí una foto de una púa en un surco, en cómo está esculpido ese surco, en la forma de la pared de ese surco es donde está grabada la información, ¿sí? Y en la foto de la derecha vemos una máquina moderna, digamos, de grabación de vinilos, ¿sí? Para hacer el máster, eso pues es todo un proceso complejísimo, pero básicamente tiene unas bobinas que cuando pasa la corriente por ahí, eso mueven la punta del torno ese y van esculpiendo esos surcos con esa información grabada ahí. ¿Sí? Esto es obviamente muy simplificado, pero da una idea de cómo es el proceso de grabación. Y si nos vamos a la grabación magnética, lo que tenemos es una cinta que se va moviendo, que tiene adherido una cinta plástica, que tiene adherido un material magnético, ¿sí? Y después tenemos estas tres estructuras que son cabezas, unas cabezas magnéticas que actúan como si fueran transformadores, ¿sí? Entonces, por ejemplo, la del medio, que es la cabeza de grabación, cuando pasa una corriente proporcional a la onda que queremos grabar, eso genera un flujo magnético que está dado en el núcleo ferromagnético, pero ese núcleo tiene un pequeño entrehierro, un pequeño gap, que hace que cuando se llegue ahí el flujo, eso va a ampliarse, a hacer una trayectoria mucho más amplia que cuando está en el núcleo magnético, ferromagnético. Entonces eso va a penetrar en la cinta y va a magnetizar todas las partículas que están siendo transportadas, ¿sí? Entonces va a quedar grabado en esa cinta, en la magnetización de esas partículas, va a quedar grabado una señal que es proporcional a la corriente que pasaba por estos. Al momento de la reproducción, lo que sucede es algo similar, solo que al revés. Esas partículas van a inducir un campo magnético, ¿sí? en la cabeza de reproducción, y ese flujo magnético, ese campo magnético va a inducir un voltaje, que va a ser proporcional de vuelta a la señal que queríamos grabar, y de esa forma se reproduce. ¿Sí? Además de toda esta complejidad electromagnética y de la composición química de la cinta, tenemos que está todo el sistema electromecánico de movimiento de la cinta, ¿no? Tenemos un motor que mueve uno de los carretes que entrega la cinta, otro de los carretes que la recoge, después hay un rodillo ahí con el capstan que hace que aprieta la cinta y se mueve para que eso gire a la velocidad correcta. Entonces, en la interacción de todas estas cosas es que van a aparecer problemas en la base temporal, ¿sí? En cómo el tiempo es grabado en ese medio. Entonces les propongo escuchar ahora una grabación moderna, digamos, que fue editada en CD, pero que fue grabada en dos grabadores distintos, ¿sí? En un caso es un Revox A77, que es un grabador semiprofesional, pesa como 15 kilos y tiene 3 motores. Y el otro es una comparación bastante injusta, es un Uger, que es un grabador portátil, que puede ser operado a baterías, que pesa 3 kilos, es una cosa portátil para lo que era la década del 60, y tiene la particularidad de que tiene varias velocidades, tiene 7,5, 3,75, 1,78 y 15, 16avos. Entonces la idea es compararlos para ver cómo empiezan a aparecer los problemas de la base temporal. Les pido que se concentren sobre todo en las notas agudas de la guitarra, que ahí es donde más se nota.
Canta mi mamá la pobre, batiendo la ropa con golpes así, y el agua clara del...
Bien, esa era la grabación con la Revox A77, una grabadora semiprofesional, una calidad bastante buena. Ahora vamos a escuchar la Uger. Está un poco saturada la grabación, eso es culpa del operador, en este caso yo, pero bueno, nada, no estuvo, el nivel estaba un poco alto.
Canta mi mamá la pobre, batiendo la ropa con golpes así, y el agua clara.
Vieron que la estabilidad de las notas es mucho menor, y es una comparación muy injusta, el otro tiene 3 motores, este tiene un mismo motor que mueve todo, y ahora lo vamos a escuchar a una velocidad 4 veces inferior.
Canta mi mamá la pobre, batiendo la ropa con golpes así, y el agua clara del...
Bien, nada, al ir bajando la velocidad se tiene mucha menos inercia, es mucho más difícil mantener una velocidad constante. Y bueno, y empiezan a aparecer esos problemas de la base temporal, ¿sí? Eso esos problemas también pueden aparecer por otros motivos, por un problema de alimentación, una caída de tensión puede hacer que incidentalmente baje un poco la velocidad al momento de la grabación o de la reproducción. Puede pasar que algunos componentes se deterioren, eso lleva, no sé, el rodillo es de goma, esa goma se reseca, no hace buen agarre con la cinta y empieza a fallar. O puede ser el medio de grabación que también se deforme, que se deforme la cinta, se estira el eje temporal, ¿sí? Entonces, pensemos un poco cómo se modela esto, ¿sí? Entonces, podemos pensarlo como una deformación no uniforme del eje temporal. ¿Sí? Entonces tenemos ahí esa ecuación en donde X sería la señal original, XW es la señal deformada, y GWT es la función de deformación, es esa función roja que está ahí graficada, ¿sí? En comparación de la negra, que sería un caso de no deformación. Y de forma equivalente podemos definir la curva de variación de pitch, que es la con la que más vamos a trabajar, como la derivada de esa función de deformación temporal. ¿Sí? Entonces ahora, pensando un poco esto, podemos tratar de explicar por qué se perdía esa resolución en frecuencia, por qué se empezaba a escuchar todo menos definido. ¿Sí? Entonces, esos cambios de velocidad, si los suponemos periódicos, podemos pensarlo como si fuera una modulación en frecuencia, ¿sí? Entonces, si hacemos el caso particular para un tono, imaginemos un parcial de la guitarra, una cosa bien simple, que podemos calcular, ¿sí? Ahí tenemos que entonces WC sería, omega C, perdón, sería la frecuencia del parcial S de la guitarra, y omega M sería la frecuencia del defecto temporal, ¿sí? De las variaciones temporales. Entonces, cuando vemos el espectro de eso, lo que tenemos son esa especie de parciales, que en verdad no son parciales porque están centrados a la frecuencia del FC, a la frecuencia del parcial de la guitarra, pero que empieza a desparramar energía para todos lados a frecuencias múltiplos de FM, ¿no? FC más FM, FC más 2FM. Entonces eso explica un poco por qué es tan destructiva, ¿no? Este tipo de distorsión, porque eso, en vez de haber un solo componente, aparece ahí toda una cosa desparramada. Bien, entonces veamos cómo podemos hacer para mitigar esto, para tratar de mejorar un poco estas grabaciones. Entonces, los métodos que hay tienen dos etapas. Una etapa de extracción de la curva de variación de pitch y otra de muestreo no uniforme. ¿Sí? Empecemos por la etapa, por la segunda, la de muestreo no uniforme, para entender cómo es que funciona. ¿Sí? Nosotros cuando tenemos la digitalización de esa grabación, lo que tenemos son muestras equiespaciadas del audio, pero resulta que esas, como se deformó al momento de la grabación, hubo una deformación del eje temporal, esas muestras no están donde deberían estar, sino que originalmente esas muestras están corridas, están en otro lugar. ¿Sí? Al correr esas muestras, al moverse, se mueve la señal que representan, ya no es la misma señal. Y lo que nosotros queremos recuperar, ¿sí? La señal que tenemos acá abajo es la señal, la que efectivamente pasó, con esas muestras corridas, todas hechas con un muestreo uniforme, que podemos asumir. Entonces, lo que nosotros debemos hacer es remuestrear esa señal, ahora sí, a una tasa uniforme, que es la que queremos, y para eso lo que vamos a hacer es interpolar, usar algún tipo de interpolación que nos permita calcular cuánto valen las muestras azules, estas, en función de las muestras rojas. ¿Sí? Hay muchos métodos para hacer eso, pero se puede usar un sync enventanado con más de 20 muestras, y eso nos da relaciones en el desarrollo mayores de 80 decibeles. Así que eso lo podemos dar como solucionado, digamos, o relativamente bien solucionado. Pensemos ahora cómo hacemos para extraer la curva de variación de pitch. Entonces, hay dos tipos de métodos. Uno que unos que tienen una referencia y otros que solo con el material, a partir del propio material, del propio audio, tratan de inferir esa curva, ¿sí? Básicamente tiene algún tipo de hipótesis de estacionariedad y se usa un modelado estadístico o modelado sinusoidal haciendo un tracking de los parciales, o se busca el centro de gravedad del espectro para encontrar esas relaciones. Ese espectrograma ahí, ¿no? Tenemos frecuencia, tiempo y cuanto más claro, más energía. Ese espectrograma es una grabación de piano, ¿sí? Es una grabación de piano toda deformada, ¿no? Porque el piano no tiene ningún tipo de vibrato ni nada, deberían ser líneas horizontales. Entonces no es muy, o sea, cumple la hipótesis de estacionariedad, entonces no es no sería muy raro pensar que si yo hago un tracking de cada uno de estos parciales, los normalizo, hago un promediado de eso, yo pueda calcular, obtener una curva de variación de pitch que se acerque bastante a lo que fue en realidad, ¿sí? Pero tiene algunos inconvenientes, ¿sí? Por ejemplo, esta es la grabación de Amalia la Vega, donde Amalia la Vega canta con un vibrato precioso, y acá tenemos los parciales de la guitarra, ¿no? Acá viene un parcial de la guitarra que se mueve como si fuera un bend, así que no va mucho con el estilo. Entonces ya la forma de trabajo anterior ya no nos sirve mucho, y acá deberíamos usar algo más asistido, en donde diríamos, bueno, esta porción de acá del espectro sí debería ser estacionaria y la demás no, y hacer una cosa asistida, ¿no? Sería difícil hacer algo automático, ¿sí? Entonces, estos métodos tienen alguna ventaja, que es que no dependen de nada más que del material, y tiene algunas limitaciones. Por ejemplo, no se puede corregir la altura global, digamos. Si la grabación está fuera de velocidad, o sea, toda corrida, no sé, un semitono, un par de semitonos, este método no nos permite corregir. El otro tipo de métodos se basan en tener una referencia, ¿sí? Entonces, si existiera alguna señal que al momento de la grabación fuera grabada junto con la señal de audio, y que nosotros pudiéramos saber qué características tiene esa señal, esas dos señales, la de audio y nuestra referencia, se van a deformar de la misma forma. Entonces, a partir de la referencia podríamos inferir cómo es la deformación del audio. Entonces, una de esas opciones es utilizar la interferencia de la red eléctrica, ¿sí? Acá hay un espectrograma de una grabación que vamos a escuchar al final, en donde no solo hay una interferencia, sino que hay dos. Esto probablemente se deba a una regrabación, ¿sí? Pero bueno, si uno mira la que está más baja, la que está ahí, estoy viendo acá el segundo parcial, ¿sí? La que está cerca de 90 por ahí, parece ser la correcta, la que es más coherente con la alteración de los parciales, ¿sí? Entonces, haciendo un tracking de esa interferencia, calculándole la frecuencia fundamental, uno puede corregir la grabación, ¿sí? Bueno, eso sirve para cuando tenemos cosas de no muy alta frecuencia. Este método sí nos permite hacer una corrección global de la velocidad. No siempre está presente, una grabación de estudio no tiene interferencia de la red eléctrica. Por suerte, por suerte y por desgracia, algunas grabaciones de archivo musicológicas sí lo tienen. Y se solapa, esa interferencia muchas veces se solapa con el contenido de audio, entonces hacer una extracción de eso es más delicado. Pero es posible y al final vemos cómo suena. Y un tercer método y último es utilizar lo que se llama la señal de polarización, el bias de las grabaciones, en el caso de grabaciones magnéticas, que lo que se hace es, se usa un oscilador de alta frecuencia, más allá de la frecuencia de audio, que lo que hace es linealizar la respuesta de este transformador, ¿sí? Entonces, de esta cabeza de grabación. Entonces, muchas veces esa frecuencia queda almacenada en la cinta, y si uno la puede recuperar, ahí tiene una señal de buena calidad para poder hacer este tipo de correcciones. reproducciones. Ahí tenemos un ejemplo. En verdad esto es una interferencia, es muy difícil conseguir esa señal porque necesitas conectarte derecho a la cabeza de reproducción. Si eso pasa por el filtro de audio del equipo ya no te sirve. Es muy sensible al alineamiento de la cabeza con la cinta, no es fácil, pero bueno, la idea es esa, ¿no? Tenés una interferencia de alta frecuencia, está fuera del espectro audible, si uno puede hacer el tracking ahí, está perfecto. No nos va a servir en general, a menos que conozcamos con qué grabadora fue hecho y cuál es la frecuencia exacta para hacer una corrección global, pero es un método que es bien interesante. Y bueno, ya estoy ahí de tiempo. Así que capaz que nada, menciono esto nomás, que lo que no hay es una buena evaluación de estas curvas, de la extracción de estas curvas. Siempre en la literatura la evaluación es escucha crítica, entonces habría que hacer definir algunas métricas y tener una base de datos para ver la performance de esto. Bien, nada. Entonces, como la distorsión de la base temporal afecta muchísimo la calidad de las grabaciones, la importancia de mantener los soportes originales, es importante y no, ni siquiera nos imaginamos pueden. Y que los métodos que acá se presentan en verdad son complementarios, ¿no? Que uno tiene que ver la coherencia que hay entre materializado, con la interferencia de la red eléctrica, con el vías, y cuando todo eso cierra uno siente que todo es coherente, digamos, si no, siempre queda la sensación de que hay algo raro. Y bueno, el último de la evaluación. Si quieren les muestro, bueno, les dejo links, ahí hay software comercial que hace esto, después si tienen lo bichan, si da el tiempo me preguntan, si no después, referencias, y les quería mostrar un ejemplo rápidamente. ¿Se da el tiempo, Magda? ¿Sí? Bien.
Dale.
Sí, rapidito. Un minuto dura, un minuto cada uno. Entonces, esta es la señal.
Estilo por la señora María Rodríguez de Santangelo.
Estás muteado, Nacho.
Gracias, Martín. Ahora escuchamos la otra versión, que es restaurada utilizando la interferencia de la red eléctrica. Ahí.
Estilo por la señora María Rodríguez de Santangelo.
Bueno, eso nomás. Muchas gracias a todos por escuchar. Y
Very good.
nada.
Thank you,
Si tienen alguna
Ignacio.
pregunta. Muchas gracias.
Capaz que dejamos las preguntas para el final, que estamos un poquito
Sí.
pasados.
Sí, sí.
O escribir al chat también. Sorry, I'm
Yes.
going to switch to English again.
Okay. So let's move to the next presentation by Pablo Cinemanas. So Pablo.
Okay. Hi, let me share my screen. Let me share computer sound. Okay. Okay, can you see my screen? Okay.
Yeah.
Okay. Okay, well, my name is Pablo Cinemanas. I am a PhD student at the Music Technology Group in the Universidad Pompeu Fabra in Barcelona. Before I started my PhD, I had obtained my bachelor and master degree in Universidad República. And today I'm presenting part of my work during that I've been doing during my PhD. And in particular, two interpretable deep learning models for sound event detection and classification. So we are using sound recognition technologies for several applications that have a strong impact in human lives. For instance, we have self-driving cars, surveillance, machine for monitoring, and even healthcare applications. However, most of the system use of in these applications are black boxes. So the black box nature of these models may produce unintended effects, such as reinforcing inequality and bias, being vulnerable to adversarial attacks, and also these black boxes are hard to debug and troubleshoot. And therefore, there is a recent surge of research in trying that the model explain the prediction that they made, and a field known as interpretable machine learning. So we want try to open these black boxes. And this is especially important when high stakes decisions are involved. For instance, like the applications we mentioned before. There is a lack of research in the audio domain in this interpretability field. Most of the work in interpretable machine learning follow a post-hoc approach. This means that they try to explain a black box model, for instance, using a proxy model that tries to imitate the input-output behavior of the model. Typically, this is a linear approximation of a nonlinear model, so it can fall short of providing reliable explanations. Rather than producing explanations of black boxes, we can try to design intrinsically interpretable models. Those are models that are interpretable by design. So we design models that are actually interpretable. By adding specific components, one can, let's say, strive for rendering some form of interpretability. In this sense, we have proposed the audio prototype network. This it has two main parts: an autoencoder and a classifier. So the role of the encoder is to represent the input in a latent space of user features. Then we have the decoder to transform this latent space back to the input representation. And the classification is based on similarity measure, a frequency-dependent similarity measure between the encoded input and a set of prototypes. And then a weighted sum layer controls the contribution of each frequency bin to some final similarity. This is finally connected to the output in order to get the predictions. Note that we can convert these prototypes to the input representation by applying the decoder, so we can see the prototypes and listen to them. Let me. Okay, sorry, this is working. This isn't working. I have some problems with Google. I don't know why. But yeah, okay, you can imagine. So those are prototypes that are actually similar to data instances in the dataset, and this is an urban dataset. And then we also devise methods for the automatic and manual editing of this model. And this is a screenshot of a web application to manual edit the prototype, so you can remove or you can add prototypes as you want. Also, in the paper we show that we can improve the accuracy of the model doing this kind of editing, even outperform the most competitive baselines. So this kind of illustrates that interpretability may also help to improve the models, not only to give explanations. Well, this is only to show that the results are comparable to the baselines. In 3 different contexts, we have environmental sounds, music instrument classification, and speech classification. And so this network achieves compelling results when applied to speech, music, and environmental audio for problems with a single class label per audio clip. So when we try to classify a new instance, the network calculates the distance to each prototypes and makes a prediction based on that distances or that similarities. And when we have a polyphonic setting, like when we have this sound event detection problem, when we want to detect all the sound sources present in the audio, but also give the onset time and the duration of each source. And this is of course a more complicated problem, and we have overlapped sources. And when we have these kind of problems, we need that a data instance with simultaneous classes has to be close to those prototypes at the same time. So this is difficult in practice and it's challenging in practice. So this motivates another model that we are proposing. We are presenting in the conference decades this year. This is an interpretable model for sound event detection. We use the same autoencoder from APNet, and we also have an encoder, another encoder to extract M attention maps. Each of these attention maps is kind of related to one prototype, one local prototype in this case. So these prototypes represent one point in the latent space, and this represent a patch in the spectrum. It's not the full spectrum, only a patch. And we convolve the attention maps with the prototypes in order to get a reconstruction of the latent space. So the attention maps kind of try to position every prototype in order to get a good reconstruction. And we can also use the decoder from the upper branch to get the reconstruction in the input representation, so we can inspect if the reconstruction is good or not. And so the classification is only based on these attention maps. So we first average the time dimension, and then we use a dense layer to connect these mean attention maps to the output. So this figure shows the results of our model compared to the baselines, and we show that we got same results, but with fewer parameters. And also for each data instance, it is possible to extract the corresponding attention maps to provide an explanation of how the model makes its predictions. Note that the model can detect simultaneous sound events whose energy is kind of concentrated in different frequency bands. Since the attention maps are designed to reconstruct the latent space and are the only information used for classification, these representations are the inherent explanation of how the network makes its prediction. Okay, I think this is working here. Okay, no. And to conclude, let's summarize the key points of this presentation. We have presented 2 interpretable deep learning models, one for sound classification task and the other for sound event detection. The proposed models provides faithful explanations in the form of prototypes in the first case, and attention maps and prototypes in the second case. And the proposed models achieves encouraging results which are comparable to the state of the art, and this kind of contrast with the extended assumption that there is an avoidable trade-off between interpretability and accuracy. So we can have both interpretability and accuracy at the same time. So that's it. I think was faster. Thank you. If you have any questions, I don't know, maybe at the end we say, right?
Thank you, Pablo. Yeah. So let's move to the next question. Sorry, presentation. Magda, all yours.
Yeah. Okay. I have questions about this, but we'll ask later. Okay. I'm sure. Do you see that? Do you see only the slides?
Yeah, on the slides.
That's good. Okay, so hi everyone. My name is Magdalena Fuentes. I'm a postdoctoral researcher at Marl, New York University. I'm in New York right now, but I'm a former Facultad de Ingeniería student and somehow teacher as well. And like I did my degree, engineering degree there before I moved to France to do the PhD, and then here. And as Safar said, moved all over the place. I'm going to be talking about some ongoing work we have with Martin, Pablo, and other people from NYU as well. Bear with me, these are ideas that we're exploring, and like if you have any questions, I'm happy to answer. I might not have all the answers, but we're happy to discuss and hear opinions about it. So the topic I'm going to talk about is localizing sounds in urban settings. So first, let me give you some motivation of the problem, why we care about this. And we care in general about understanding real scenes through sound. That meaning knowing what's going on, knowing what is producing a sound, what object, is it a dog, is it a person, is it a vehicle? Where is that sound being produced? So what's the relative location of the sound source with respect to the microphone? And how is that source moving, if it is moving at all? Is like moving fast, is from left to right, or stuff like that. And this has many applications in general about like smart devices and like urban monitoring stuff, but the applications that we care about are more urban related. I'm in the Center of Urban Science and Progress as well at NYU. And in this case, we care about understanding urban traffic scenes through sound. So same questions as I just mentioned, but in the wild, like in the city, right? Putting microphones in the city and trying to answer those questions. And one of the reasons why we care about this is because that could lead to, like, putting microphones out there is low cost, so it's kind of cheap, and is much more privacy preserving than putting, for instance, cameras, or is much more difficult to identify a person or a particular car through sound than through image. And that could lead to nicer and like still effective mobility system and smart structures. So this is kind of the motivation of what we are looking into this problem. So to give you a bit of context of like what's out there right now, localizing sources is not a new problem in this audio community, especially in the signal processing community and communities such as like ICAS or DKs. But the way that it's done like for instance, in the challenge in this case, is mostly using datasets that are synthetic, meaning that, for instance, a microphone is put in a room and some speakers that you don't know exact location, like distance, the elevation of that source with respect to the microphone, the azimuth, so the angle with respect to the center of the microphone and stuff like that is very controlled. And even more, you don't have many challenging scenarios where you have more than one source of the same class, let's say 2 dogs at the same time. So this is is a challenging problem anyway. So that's why they are doing it in this like controlled way. But that is very, very hard to do in the wild, or like in real world applications or urban applications, where you have no idea, no ground truth at all of like what's the distance, elevation, or azimuth of vehicles there. And you cannot get that easily either, because you cannot just like put all a bunch of sensors on top of like cars, or like, I don't know, it is very costly. I can't really imagine how to do that. So we have to think about the problem and see what we can do and we cannot do in these settings. So the current limitations on this problem, when we start looking at it, is like we didn't find data sets or well curated resources to train or evaluate any model on like localizing these things. And moreover, as I was just saying, we didn't find many people looking at it. So the problem is still a bit open, and we don't know really much what is possible and what is not. So it was kind of like quite interesting, but quite open. So we started looking into this, and we did took three steps, small steps, to start looking at this type of problem. We put together a data set, which we called Urban Sound and Sight, Urbansas, for not having a better name. We put together a small, to be improved a lot, baseline based on what the community in the case has been doing. And we looked at the problem of how evaluate these models in this new setting. So we look at some evaluation metrics from the computer vision community and try to come up with something over there. So that's what I'm gonna be talking about. So Urbansas, I'm gonna give you an overview. This is not public yet. We submitted it, and we'll wait for a decision for some months still. But roughly, Urbansas is an audiovisual dataset that was put together from existing datasets, in particular two public datasets, and also an extension of one of them that was not public. Those two datasets are the mapped dataset, Montevideo audiovisual dataset, that Pablo and Martin put together some time ago, that has a lot of recordings from Montevideo and like video and audio. And the other one is from Tampere. From Finland, the audio group there has a bunch of like super cool datasets, and they're working a lot in this type of problems. And they released recently an audiovisual scene analysis dataset. So what we did is like, we took those public datasets, and Martin and Pablo also curated much more data from like similar to MAP that was not public. And we also curated that, and it was like a 15 hours of material, which we annotated 3 hours. And we annotated bounding boxes of the vehicles moving and audio labels. In particular, we focus on vehicles because it's what is kind of like predominant in urban settings, that is moving and producing sound. And we focus on cars, trucks, motorbikes, buses, and also added a label that says off screen, which is like those vehicles that you can hear, but you cannot see. And also some clip level metadata, such as location, if the scene is very busy, or if it has the video has poor lighting, so we can investigate the methods better. And one thing that's important about urbances is that it really shows the problem as it is in reality, or we try to approximate, in the sense that the first two plots that you see, there is a bit imbalance in the classes. There are a bunch of cars. They are all together, sounding at the same time. And there are like scenes, like there are frames and like clips where there is only one car passing at a time, but there are also many scenes where there are multiple things going on, and it's complex. So we will be having a lot of fun trying to make something work in this scenario. This is a video. It's not maybe the best video, but it was like one of the ones that I had handy, and I think it's good in showing the complexity of that we can have in these scenes. The blue bounding boxes are cars. I think at some point there is like a motorbike, and at some point there is an occlusion because the person that's recording, this is from Tampere, decided to like do some move, and the hand appears. You'll see it, and like there is an indication of occlusion in the scene. So this is fairly complex, and also the guy's moving, and that's an occlusion. So it's very real, and this is courtesy of like Tampere group. So the problem now, the formulation of the problem is, okay, we give up this idea of we are going to have a perfect ground truth with like distance and angle and like azimuth and whatsoever. So what can we do? Now we have a microphone and a camera in the same position, and we know the field of view of that camera. So what we are going to do is to infer the position of the vehicles with respect to the microphone somehow using the video. And for that is that we use the annotations of the bounding boxes that, as I said, have some like information such as occlusion and stuff like that. So what we decided is to, we didn't define azimuth in the same way as the decades community does it, because we don't actually have an azimuth, but we have an approximation of how the thing is moving, giving the image. So we define the ground truth in two ways based on the position of the bounding box. One is, okay, like I think, well, I don't know if I can annotate, I don't think so, but I don't know if you see there's a very faint bounding box there, but basically the picture of the right is showing that we are like dividing the image in different regions and trying to say, okay, this car is moving from this region to that other region. And we approximate that in two ways. The figure on the right, we approximate the position of a car just by the middle point of the bounding box. In that case, you have two cars. And the reason why the black car is not annotated is because it's parked. So you also have that in the data set, which is like things that are there but not producing sound, and things that like look the same as like the other objects that are producing sound. And the image of the left is the same idea, but instead of approximating the position of the car and saying like it's exactly this point in the like the central point of the bounding box, we say, okay, it is in this region, and we take the whole bounding box as indicator of position. So we are kind of exploring different ways of defining the problem. I don't know if, am I going too fast? Or people are, no? Yeah, okay, good. So how do we evaluate this? The metrics on that are usually used for this problem assume that you have like assume you have all this information, and also that there aren't many, more than one instance of a class, so not two cars at the same time. So we need to move out of that. And at the same time, we wanted to make some connection to the computer vision community, because they have been looking into the problem of sounding sources in videos. So because we have the inspiration from bounding boxes, what we propose to do is to use a metric that's intersection over union, which is basically a ratio between your estimated bounding box and the ground truth, or your estimated mask and the ground truth, over the union of the two. And we propose to compute one per class. So we will have like a way of understanding how good the model is at detecting there is a class, there is this vehicle of this particular class, and how good is at saying those regions. So instead of the bounding boxes, what we did is apply that metric in the regions. So instead of like the box itself, it's just like, how good am I telling, how good is my model telling where things are located with respect to these regions. So we built this first baseline, this first model to try to do that, which we based on the baseline of the DK's task 3, I think, the localization one, which I'm not gonna get into details, but basically takes a stereo, like the original one takes 4 channels and estimates azimuth, distance, and elevation. Our one takes stereo, because I didn't mention this, but Urbanza's is stereo. And convolutional layers, blah, 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 recurrent layer to integrate information. And it produces a tensor that basically means that for each class, which regions are activated at a time, that for the entire clip. And that you would expect to see, like, if there is a track that's moving from left to right, you would expect to see that the network will tell you, like, oh, there is like this class at this region, and then it's moving from here to there. So that's what we would expect. What do we get? We get this. Which is kind of trying to do that, but still activating quite like more things. And like basically we had to adjust the threshold to see when things are going, but it's getting somewhere there. And the metrics that we got compared to random here means having a random baseline predict a couple of regions randomly for different frames with a certain distribution. We do better than random, that's always good, but the problem is very hard and we still have a lot of room to improve. So that's more or less what we've done. And what we have to do still, which is a lot, but basically the things that we're working on next is to improve the baseline and do a full analysis of results in Urbanzas that we didn't have the time to do when we wrap up this paper, that we were only presenting the data set. And the reason why that's interesting is because it will bring, Urbanzas has the information to understand how models are failing and like how like different scenarios affect, or different configurations affect the performance of these models. So there's a lot to do there. We are looking into self-supervised embeddings. So trying to get some embedding that is good for localizing sounds in urban settings. That's also a lot of fun. Pablo mainly is going, like Pablo and Martin, as I said, were involved in this, and Pablo will be looking at, and we will be looking at Pablo looking at interpretable models for localizing sound sources in images as well. And then we are gonna, through this process of defining the problem and seeing how we can get the evaluation metrics and stuff, we learn a lot of like the complexity of evaluating this as well. And we are gonna dig deeper in the metrics and the problem definition itself. And I think that's all. So thank you. And I lost my pointer, so I cannot stop this. There you have.
Great. We are running a bit of delay with the agenda. So I guess I don't know if there is any question. We are going to create some groups for discussion. So in the meantime, maybe you can ask. I'm going to stop the recording now.